So in this video we're going to talk about the effect of temperature on rate. Now if you go back and watch the video about the introduction to Maxwell Boltzmann, we did mention this briefly. So what I want you to do is think about the features that you drew and redraw a Maxwell Boltzmann curve, just a normal Maxwell Boltzmann curve on this axis. So remember, we're looking for those key features. Does your curve start at the origin? Does it never rejoin the x-axis? Is the peak to the left? Because not many particles have, the energy of the most particles is quite a low energy. So that's our original curve. What I want to do now is draw on a second curve for a higher temperature. Then we're going to look at the key features of that. So I'm going to change colour and then draw a second curve at a higher temperature. So there's my second curve at a higher temperature. So what key features are we looking for? We're looking for the curve still starts at the origin. No particles have zero energy. We want the peak to be lower and to the right of the original peak. And they will be really looking for that in the exam. So the peak is to the lower and to the right of the lower temperature curve. Now if you were asked to sketch on there a curve at a lower temperature than our black one, we would have to do the opposite. I'm just going to do this temporarily. We'd have to start and go higher and to the left. Now I'm going to rub that off, but that would be a temperature that was even lower than that first one. So we'd keep going higher and to the left if we were going lower in temperature, and lower and to the right if we were going higher in temperature. So that's our second sort of feature. What else can we say about this? Well, we need to be able to say that the total area under these two curves is identical, because we haven't changed the number of particles, just the energies that they have. So the area under the curve is the same for both curves, but the number of particles at the higher energy end increases. So why is that important? Well, if we mark on our activation energy and shade it in, and if it stays in the same place and we shade that in, look how many, it's almost like doubling there, the area under the curve with energy greater than the activation energy. So many more collisions are going to be successful. So the shaded area that's those with energy greater than or equal to the activation energy increases. So many more collisions are successful. Okay, so in general, a very small increase in temperature, just 10 degrees, so warming it up from room temperature to say 30 degrees, is going to cause the rate to roughly double. Why does such a small increase lead to a large increase in rate? And it's all to do with the size of that increase with particles with enough energy to undergo collision. So let's just write that in. So many more particles have energy greater than or equal to the activation energy, so many more collisions are successful. And there is just a note at the bottom there that although the rate of collisions does increase, it's insignificant, and that is why back at the beginning of this pack we talked about not talking about collision theory when we're doing temperature and catalyst, but just talking about activation energy.